So now next one we are going to see about photodiode. The normal diode, you know, it is a device which will work in different waves in forward bias and reverse bias. And for a normal diode, the input is going to be voltage. You are going to give voltage to your diode, and this voltage is going to set up a strong electric field across the diode, right? And all the conventional PN junction diode work with electrical input, which is voltage. But photodiode is a light sensitive device. It is also called as photodetector. So it is going to convert the light signals into electrical signals. So this diode is going to work with light. Input is going to be light. So remember, this photodiode is a conventional diode, but it is going to work based on the input light. So the construction and everything is shown in the figure. You can see here the PN junction diode. It is a normal PN junction diode, but you are going to focus light on the depletion region. You are going to focus light on the depletion region. Okay, and this PN junction, this photodiode is going to work in reverse bias. Very, very important thing. This photodiode is going to work in reverse bias. So reverse bias means you see P type will be connected to negative, N type is connected to positive. So the holes will be glowing, going to the negative of the battery. The electrons will be attracted towards the positive of the battery. So the depletion layer width will increase. So conventionally with this voltage input alone, the majority carriers cannot cross the depletion region. Adukada we are giving energy in the form of light. So by acquiring the energy from the light, the majority and minority carriers can easily cross the depletion region in reverse bias and produce current. Okay, that is the working of your photodiode. So the diode is same way made of semiconductor PN junction diode, and it is kept in a plastic or glass casing. So the cover is designed such that the rays are allowed to fall on one surface across a junction. So you are going to ensure that the light is going to be focused on the depletion region of the diode. So the remaining sides are painted so that it does not allow the penetration of light rays. Even though light is going to fall on the entire device, only the region near the depletion region is ensured to capture the light. Other regions will not allow the light to penetrate inside. So that's for focusing that only you will be having a lens. See here, you have a lens. This lens is going to focus the light rays exactly into the depletion region. You know, simple example, you focus the sun rays using a lens and the paper starts burning, right? Same way here, you're going to focus the light into the depletion region so that the carriers will acquire this energy from the light and they will cross the depletion region easily, even though you're going to have reverse bias condition in your diode. So lens will permit the light to fall on the junction. When light falls on the reverse bias junction, electron hole pairs are generated, and the movement of electron hole pairs will result in the current flow. Okay. So since this is the current produced because of light, that current is called as photocurrent. It is called as, in conventional diode, it is a normal forward bias or reverse saturation current, you call it, but here you call it as a photocurrent. And this current depends on how much is the intensity of light and how much charge carriers are generated. So the intensity of light is very, very large, then the current will also be large. And one more thing, the number of charge carriers produced because of this light falling on depletion region is going to be large. The photocurrent is also going to be large. And one more thing which is going to affect the frequency affect the current is going to be frequency of light falling on the photodiode. Instead of calling it as frequency, for light you will not call frequency, you will associate light with a term called wavelength. So the photocurrent also depends on what wavelength of light, or to say it in simple terms, what color of light is falling on the diode. Because some colors will have large energy and they will produce more charge carrier. Some colors will have energy band gap to be less and they produce less charge carrier. So the amount of photocurrent is going to depend on the wavelength of light falling on the junction of the diode. The magnitude of current under reverse bias, largely reverse bias. So this diode is going to work only in reverse bias. So remember, major differences: conventional PN junction diodes will work in forward bias, but this photodiode is going to work in reverse bias. That is the major difference. And the symbol you see, it is a normal diode, and you have to focus that light is falling on the diode, so it becomes a photodiode. So this is the symbol of your photodiode. And magnitude of current and the large reverse bias. So you will be using the conventional diode current equation. I is equal to Is plus I naught into e power 1 minus e power v by eta Vt. So I naught is the reverse saturation current, and Is is the short circuit current, which is produced because of the light falling on your device. You know, V is the reverse bias voltage, eta is the device parameter, and Vt is going to be the equivalent temperature, thermal voltage. So the reverse the VA characteristics of PN junction diode, the photodiode is given here. You can see it is in reverse bias. So we have drawn the graph in third quadrant. It is reverse bias. Okay, so V is negative, I is also, since it is reverse saturation current, it is going to be negative. You can see as you are going to increase the light intensity, the dark current, the amount of dark current flowing through the device is also going to increase. So that's what I have told you. The dark current or the photo current depends on how much amount of light intensity is going to fall on the device. So when no light is falling, that current is called as dark current. See the first graph, 0 lux. Lux is the measure of luminance. So luminance means brightness. 0 lux indicates no light is falling on the photodiode, so it is corresponding to dark current. So even when no current is applied, you have some minimal amount of current, reverse saturation current flowing through your device because of minority carriers. That current is going to be called as dark current. So as you increase the luminance of light intensity falling on the photodiode, you can see dark current, the photo current will also increase. So it is increasing. Dark current is 20 microamperes. So as I increase my light intensity from 0 to 800 lux, my photo current is increasing from 20 to 100 microampere. So it is increasing 5 times. Correct. So because of light intensity falling on the device, the photo current also will increase proportionately. See here, that is what is given. The reverse saturation current increases directly proportional to the level of illumination. So how much light you are going to focus, that much level you will be having the increase in current. Even when no light is applied, you have some current because of minority carriers. That current is called as dark current, which is flowing through the device. So when you when you consider the materials used for making this diode, so you know the silicon and germanium are used, but germanium is not preferred because germanium has a very high dark current compared to silicon. The dark current is just like noise. The current light illadappa some current is flowing means that is just like whatever is unwanted current, or I can say it is going to be noise. So when you compare silicon and germanium, germanium is going to have a very high level of dark current, and it is not preferred when you're going to fabricate photodiodes. So I'm going to use only silicon as a material for fabricating your photodiode. So I'm not going to use germanium. No, I'm going to use only silicon to fabricate my photodiodes.